The third method that we are going to use to try to understand 4D objects is to look at their boundaries. Now, a boundary can have some pretty technical definitions, but here's the one we're going to use. The boundary of an object is just the very edge of it, whatever that means for each dimension. It is the parts of it that are going to separate the stuff that's part of the object from the stuff that is not. And the thing is, this is only going to work within the dimensions that an object has, and that's a little bit confusing. One thing we know for sure is that the boundary of an n-dimensional object will always, always, always be one dimension lower. So it will be n minus 1 dimensions. So the boundary of a 1D is supposed to be 0D, and here's a line segment. This point here, right in the middle of the line segment, is not in the boundary. Why? Because within that 1D object on either side, there is line segment. It isn't a point where there's nothing on one side and line segment on the other. So that point isn't in the boundary. These 2 points are in the boundary. On one side of the point is line segment, and on the other side, if you go in that same one-dimensional direction, there's nothing, there's vacuum. And so the boundary of this line segment consists of these 2 points, and that is 0-dimensional. There are other kinds of 1D objects, like here's an X shape, right? And none of the points that are in the middle of the line segments, and not even the point in the very center of the X, it's not going to count as being on the boundary. But these 4 points are. In one direction, there's going to be stuff. In the other direction, there's not going to be stuff. And it doesn't matter that in these crazy second dimensions or third dimensions, there's also nothing. No. We're in 1D world, and so we only get to look 2 directions. In any case, the boundary of the X shape, 4 points. Here's a tricky example. A circle. What's the boundary of a circle? If you look at any point along the circle, and you look to either side, there's going to be line segment, right? It doesn't seem to matter where you look. There's always going to be line segment on both sides. The 1D circle with no area, it has no boundary at all. There's lots of objects that have absolutely no boundary. That's totally normal. As opposed to the disk, which is like a circle, but all filled in. That's actually a 2D object, right? And if you look at points along the edge, the very edge of this disk, there's a sense that there's an inside where there is object there, and then there's the outside. It separates in from out in a very fundamental way. This is different from any of the points that are in the darker shaded area where there's part of the object all around. They are surrounded by more disks, so they don't get to be in the boundary. And so the boundary of the disk consists of that outside circle. Leveling up, the boundary of a 3D object will always be 2D. So if you think about the 3D cube, if you were holding like a solid wooden block in your hands, the boundary would be the parts that you could touch with your hands. You know that there's wood on the inside, but you can't get at it with your fingers. You may have made some paper tetrahedra in class, and when you made those were hollow when you were done, right? That was a little bit of a lie. Those weren't the actual tetrahedra, those were just the boundaries of them. And so if you were to start with this object on the right, this cross shape, that is the boundary of the cube. That is the object that we can reassemble and make the hollow cube shape like we did in class. Which leads me to ask, if you needed to, could you give instructions for assembly? That's going to be a really big part of understanding how the boundary of the 4D cube comes together. So if you had this made out of paper, maybe you understand that the 3 flaps on the sides and the top are supposed to fold towards our faces, and you can fold the bottom flap towards our face too, and that very bottom square becomes like the roof, like the part closest to our faces. And so as long as you understand that, then good, we're on a roll. So the secret here on paper is to identify which of these edges are supposed to get attached or taped to the other edges. For example, once you're done assembling this whole thing, the very top edge and the bottom edge are supposed to get taped together. And so you can color code or you can use letters, however you want to distinguish these different edges. We need to indicate that that very top edge gets glued to that very bottom edge. Now, think about that process of folding the walls up towards your face. you're actually going to wind up taping this edge to that other edge, right? The edges that I've marked B. And in fact, that's true all around. All of these pairs of edges are going to get taped together in order to hold the cube boundary together. And so I want to demark these using color or letters. Now comes a slightly tricky bit. Can you see that these edges on the sides actually become attached to parts of the roof, right? The edges marked F get taped together and they're actually going to be pretty close to our face, and the edges marked G will be the same. Every exposed edge is going to get attached to a different edge, and that's how we're going to recreate the boundary of the cube. This strategy works in 4D as well. It's pretty trippy. This is the three-dimensional boundary of the 4D hypercube. However, just like the boundary of the 3D cube that I was working with before, this is what we see after we have cut it apart partway. We have sliced some faces apart so that we can actually view this boundary in our lowly 3D world. And so it's helpful to understand which faces get attached to other faces. If we wanted to, could we reassemble this boundary in 4D world? There are different things that we can understand. First of all, these faces actually get taped together. And maybe in 3D world, you can imagine, especially if you imagine the cubes being made of something stretchy, you could actually get away with taping some of these together, right? But you won't get very far because actually all of these all around the top will get taped together as well. And here's the crazy bit. The very top square is going to get attached to the very bottom square, and that square is going to be folded around and attached to that square. It turns out we can keep going with this identification process. Every single exposed square is going to be attached to some other exposed square. And again, you can't show this in 3D world. This is a 4D object. That's why the cutting apart is so important. It helps us literally draw something on paper. Otherwise, we wouldn't be able to draw anything at all. The best we can hope for is to draw this like hypercross shape and start coloring the different squares and saying, well, look, if we were 4D people, this is what we would do to put it back together.